and we will look at some names famous in the PSI world outside of China. I'm sorry, I didn't look into China, but I know Alibaba is doing. And we are looking at how to observe pressure and how to be notified about PSI events. To end, we look at PSI, which is an extension to bringing new API from PSI into PostgreSQL. Give me 1 second. So, the distinct kind of process in PostgreSQL. I tried to set up some groups of process, what we call backend in PostgreSQL, but not only, because, for example, the first one here, Postgres, is just the father or the mother of all processes in PostgreSQL. This is the one which started PostgreSQL, and which is used then to create new backends and to create new process into PostgreSQL. So this is a very critical piece of PostgreSQL. If Postgres process is slowed down or is stalled, then most of the system is stalled because you cannot create new connections, for example. And then in the same kind of process for critical group, I define in some, I believe it was important to put Autovacuum launcher, which is not absolutely critical, it's more maintenance task, but the Autovacuum launcher itself is just here to evaluate what is going on and trigger and create and spawn new process to create and to start new Autovacuum workers, which themselves are maintenance process, but I think that the Autovacuum launcher is really critical. And then we have a new process which is logical sync slot worker, which allows to synchronize slot between primaries and replica in order to provide a failover solution, for example, for the logical replication slot. So quite important also, because if the logical slot sync worker is delayed, you may have a delay in your replication, in logical replication, or you may suffer from issue when you try to fail over or switch over. And then there is 3 main wall process. The wall, you know it, this is a write ahead log, so it's here to ensure that if the server crash or whatever happen, it can restart and safely recover all transactions which has been committed so far. And the point that the wall receiver, senders, and writer are, the writer is a process which is going to write the wall locally on the machine, on the server, to ensure that the local PostgreSQL is able to restart after a crash, while wall receiver and senders are here, as their name says, to send the wall to replica or to receive a wall from the replica. So both ways are very important. When you receive data, you want to be reactive, sure, but also the wall sender is a very critical piece, and often in PostgreSQL, the wall sender is CPU constraint, meaning that if you overconsume CPU, the wall sender is going to slow down, and it slows down everything on the replication. So protecting the CPU workload from the wall sender is very interesting. And this is one of the targets for this project. And then we have some workload processes, and I put only 2 here. The regular backend. Regular backends are the most useful. This is when you connect. Every time you connect, you create a new connection to PostgreSQL, then there is a new backend, a regular backend. So anytime you execute a query, it's via a regular backend, or if it's not via direct a regular backend, maybe you started or maybe you developed your own background worker. Background worker are very similar. They are started by PostgreSQL or by yourself, and they run in the background like a daemon, and they're able to connect to the database to do action and to offer many features. So both of them are really, I would say, workload and more end-user process. And the third group is about maintenance workers, which are maintenance process. So Autovacuum workers, which are going to manage vacuuming, analyze of the tables, but also ensuring that you don't exceed XID, XID is an identifier in PostgreSQL to serialize operation, and so at some point in the future, AutoVacuum is starting on a table to also vacuum this XID. Okay, so it's important, and when it's about XID, it becomes critical, but that's all. And the background writer is a process in PostgreSQL to be able to spread the write to the disk. You know, when in PostgreSQL we have shared buffers, which is a memory where we can store buffers which are pages from the disk. And then in those pages, which are on memory, you can write and read, but at some point we need to flush them to disk, either because we do not have enough room in the memory, or because we define by timeout, for example, that it's time to flush them to disk. And so what happens that after, by default, 5 minutes, the checkpoint writer is going to execute and flush to disk everything which is dirty on the memory from PostgreSQL. But before the checkpointer does the job, background writer can do the same thing a little bit ahead of time to ensure that there is always room in the shared buffers for your backends. And then the WAL archiver and WAL summarizer, which are just two-side process for WAL for backups. And another group for the logger. The logger is just an auxiliary process. You don't really need it. If it's down, it's down. It's not a problem. But so it's its own group. And the last one, which I didn't put anywhere yet, is the new group for PostgreSQL 18, which is I/O workers. And so this is a very good improvement in terms of design for PostgreSQL, because for managing resource, and especially with C group and PSI that we are going to look at, it's important to be able to really assign an I/O to a process, or memory access to a process. But in the current design of PostgreSQL, to access the same page of the same file, you have distinct processes who can do that. Background worker, my regular backend can do write disk, and also the while is going to write disk, etc. And so the sharing of I/O is not very good to be able to track seriously what is going on the machine. So these new I/O workers will, I hope, be able to get better understanding of the I/O and better understanding of the I/O we need to protect. So one point, well, not only one point, but one important point is that PostgreSQL is not based on threads. It's only forks. It means that every time you create a new connection to PostgreSQL, this is a new process. We create a new one, and so you only have one single action at a time on a PID, on a process. It's also very convenient because in most cases, when you execute a query, there's a single PID doing the job for you. Sometimes this is parallel work, so you have other, you can have parallelism on the execution of the query, but anyway on a PID there is only a single action at a time, no thread, so it's much easier to track and much easier to debug. And for I/O resource it's very, and for resource, for CPU, memory and I/O, it's very convenient to get this model. So what we need to figure when we want to work on this side of the story is to really understand the backends, the process we are using, what they do, what they need, and also understand your workload. What kind of workload are you doing on your database? Is it purely analytical database, where very probably you want to have a very powerful CPU? You don't need hundreds, of course, but you want very powerful CPU, so your aggregation queries are faster, because math operation will be just faster. And at the same time, you may have workload which are more transactional, and in this case, you probably want hundreds, of course, so you can serve a lot of concurrent users, and with very basic queries. Usually in transactional, you do not have a lot of aggregates, so this is not a CPU constraint on power, but more on the number, of course, to be able to serve distinct end users, because every time, one user is one process. So, some resource requirements. For the wall, write head log, which is a critical piece. this is shared sequential write. It means that there is only one single process which is going to write to the disk, to the whole stream. And the process do just a queue on memory, but they don't write to the world themselves. And then we have a large number of processes who are going to share, read and write on files. And for example, when you read and write on an index or on table, many backends in PostgreSQL can do that. Okay, so maybe I'm connecting to the server, I'm going to select from a table, so I'm going to read disk to memory, and then someone else connect and do a select, and maybe it's going to read some data from the disk and read some data from the memory, because we have a cache. And so all those read and write are shared together. If I modify a block, someone else can also update this block after me in memory, and so we share the write to the disk at the end. So it was about I/O. And for memory, we have three kinds of memory, more or less, in PostgreSQL. We have everything which is pre-allocated shared memory, so what we call shared buffers. So this is very famous in PostgreSQL. You know, when you start, you need to define shared buffers, and if you update it, you need to restart PostgreSQL. And so this is pre-allocated memory. There are work in progress to make that more dynamic, and so we don't need to restart every time, but it's not done yet, and it may make some time before it's really interesting. So we have this pre-allocated shared memory to understand. And then we have dynamic shared memory allocation, which is something very interesting too in PostgreSQL. And so since several years already, when you create background workers or your extension or whatever, you're able to assign yourself some dynamically you can get some shared segment, and you can share them with other process. So it's very convenient, but it means that we have already another scope of memory. And the third one is a per process local memory. So when you connect, you're going to do some work which is going to use the shared memories, but also do some work on your own process where you're going to use your own memory on the process. And including in that is also the memory which is going to be used to get statistics from the server and to share statistics with the server when you execute queries. I'm talking about statistics about the number of read, writes, index scan, and so on. Index. So the purpose here of PSI and all of that is to be able to observe very accurately and very correctly as much as possible the workload, because this is super important. We need to understand and to observe, to define what is expected or not, what are the requirements. You can evaluate that on paper, but getting a real observation is much better, and it can change from a machine to another machine. It depends of the application, it depends on many factors. So it's always interesting to get an evaluation, an observation of your system to understand it and to see what it needs, what it requires. So we can understand the workload, and given that we can assess how much memory, how many I/O disks we need, how many cores or how powerful cores should be to serve correctly our workload. Then we can evaluate those points, get bottlenecks. So if we have observed and assessed stuff, then after that it's relatively easy to define when we are going to overconsume resource or when we want to protect resource for some process. So PSI, precious state information, is really feedback and observability for each process on CPU I/O memory, but not only each process, more on group of process. So the huge benefit with PSI is that you can observe very fine-tune the metrics. I go on it. So with PSI, this is a kernel feature where we're going to either look at the statistics or listen at statistics, and if something is happening, we can either proactively or on a regular basis check the workload and reassign resource, or maybe we're going to limit the execution of a process because maybe it's going to consume too much and we want to slow it down to serve other processes instead. And so the idea with PSI is to be able to pause, kill process, and slow them down, throttle. Maybe one point is to say we can remove auto-vacuum configuration and let all the throttling and all the auto-vacuum tuning be done directly by PSI, because then we can go as fast as we can and just slow down when it's needed. And there are probably a lot of use cases. So first point for first introduction of PSI in Linux is in 2018, and so I put a QR code, and there are other QR codes later for accessing the resource. There are several links to Linux and open source project and just reference. And so this is official documentation, which is worth reading. It's not very long, and it's easy. It's easy. It's not a very complex documentation. On PSI, there are several actors, several people who are really involved, individuals and companies. And for instance, this is really Facebook, which has started PSI a lot. And so you will also find, well, first entries into the weekly news about that, and we'll find a link later about the documentation from Facebook about PSI. And another, so Johannes Weiner did a lot. Okay, this guy did a lot of patches provided to the Linux, and Johannes is often active on Linux development. And then from Google, Shiren Bagdasarian did provide original patches to get event notification. So it means that with the first half from Facebook already get much accurate metrics, better metrics, and then with the Google introduction we got feedback, we got event notification, which is a very good combo. And then we find on Android, so Android device and Android software, the kernel of Android, there is also the similar things from PSI, and so it allows to set up a process called LMKD, which is a lightweight daemon to manage memory on an Android device. And so it replaces the usual OM killer we have on Linux. This is lightweight and more adjusted to the workload of the Android system. It's one of the usage of PSI. And then there is Prometheus agent, which has been provided by Cloudflare, Prometheus exporter. So it's convenient, you have it on GitHub, and also it outlines that major people like Cloudflare, like company like Cloudflare, are interested by PSI and are using PSI, because this is very interesting to ensure that you're taking the most of your resources. Okay, let's go now into more technical details about PSI itself. So the basic idea with PSI is that we have a file in /proc here, but it can be another place when we are using cgroup. But by default, resource files are /proc /pressure, then IO or CPU or memory. Okay, and all three files are the same. They are very similar. The content is the same. And when we are using cgroup, we have the same kind of three files, but under another path, which is /c/fs/cgroup and so on. You will search the exact path. The point is that what inside the file is very interesting, because inside the file, when you just look at the file, you just cut the file, you will see those two lines every time for all of three. If the file does not exist or there is no information, it's because maybe the information has been, I would say, well, sorry. On PSI, you always have this information, but when you go on to controller group into C group, you may have C group where you want to look only at CPU metrics and not other metrics. So on some C groups, you don't have IO pressure, for example. It's up to you to define. But by default on the system, we have IO, CPU, and memory here. And so the first part is that you see the lines here start with the first word, some or full. And so some or full are just some or full are just explained here. Excuse me. Yeah, there is a laser point. Okay, well, the sum is just for a single task. When you have the sum line, it just means all you are looking at is related to a single process. Okay, so all the line is for a single process. And then full means that all the processes were affected at the same time. Okay, so it's really very granular and just one or everybody. Anybody which is doing something, because if we are just process which exists and doing something, nothing, it does not count. And then we have the next information on the same lines, average. And so the average are very similar to the load average, but more precise, okay? And so here we have an average of over 10 seconds, 60 seconds, and 30 seconds, 300 seconds, sorry. And where we have a feedback on the percent of time we have been stalled on the resource, okay? And this is independent from the number of CPU. So it's very convenient. We have direct metrics from percentage, and then the last part, the total, which is nanosecond cumulated cost. And so it means that here, for some process, were stalled up to 4 billion something nanoseconds, okay? And then at the bottom, 3 billion something nanoseconds, all processes were locked, were stalled. They did nothing at this time. So it means that if you use this information, average is provided by the kernel to give you already some inputs. But the most important is probably the total at the end, because it's updated every time, and you can use it to build your own average. If you want to get an average on 40 seconds or 200 seconds, up to you. You can do it. The same total also allows to better identify spike and burst. So if suddenly you have a burst of activity on the server, the total really is going to increase very quickly, and you will notice that very easily. If you look at the percentage, it will work too, but you need to wait over the period of time to get the average growing. I said nanosecond, but this is microsecond. So this average is very similar to the tool on Linux, which is the information load average, except that the load average is based on number of CPU. So when you look at the load average, you need to know the number of CPU you have to be able to get a good information. When we look at average on PSI, this is directly independent from the number of CPU. And and so also the other point is that here with average on PSI, we have the information by resource. We are maybe stalled on I/O, maybe stalled on memory, maybe stalled on CPU, but we know where we are stalled. Where with load average, we don't know that. The other big point is that on load average, the window and samples are very large. Sample by default are on 5 seconds, and an average window is of 1 minute. Okay? At the opposite, on PSI, the window is the sample is 50 milliseconds first, and then the window is from 500 milliseconds to 10 seconds. So it's much more precise, and you can have very nearly immediate reaction. Okay, thanks to the sample, which is very short. There is only one major blocker for end users when you are not root, because currently when you are not root, you can have only windows of 2 seconds or multiple of 2 seconds. So it's 2 seconds, 4 seconds, 6 seconds, but nothing in between. So the other point is, as I said, all tasks are identified by load average, where in PSI this is average per kind of problem. And so it's really much easier to get all of that. So I didn't prepare a full demonstration live, but I have some slides for that. So let's get this very simple example. In this case, we consider we have only one CPU, one core, so there is no math about the number of cores or whatever. And we are just looking at two simple tasks, task E and task B. And at time 0, they are started. And for 2 seconds, they work very correctly and there are no stall. Not on CPU, not I/O, no memory, no problem. But then, task A starts to be stalled on something. So here we can say that we are looking at just I/O, for example, and so we say, okay, some process, and we know this task A is locked on I/O, and so we have the sum line which is going to increase. We have a total of 1 second between 2 and 3, and we have an average 10% of 33% over the period. Okay? Then they keep on, and so task B here was not locked, it was working well, but then both are locked at the same time, and both are all the process we have on the server. So at this point, this is this part which is going to increase also. And so we have the information here that everything is stalled. This is very important because if everything is stalled, that nothing is running. So you have overload your server, you have something to manage. And then after that, from second 7 to 8, task A is okay and task B start to be stalled on something also. And so again, this timing is going to be accounted on total here, on same total for some process. So the sum is just for a single process, but not a single same process, okay? At the end of the story, after 10 seconds, when both processes are stopped, well, we can see that on 10 seconds, we wait for 60% of time for 6 seconds on some process, 1 second here, 4 and 1, and we wait for 40%, meaning 4 seconds on both process. So, really, this PSI, this is that. You can observe what we saw here. We can observe very conveniently, quickly, with just a cat on a file. And we have microsecond updates. Well, 50 millisecond sample, but we have updates very often. So, apparently, this is the most powerful solution we have in Linux to get aware of the resource usage. And so far it was how to look at the metrics and get information, statistics from the servers, okay, from the file /proc/pressure/IO, CPU or memory. And now we are looking at event notification. And for event notification, this is very convenient because this is the same file. So we do use the same file to read something, but also to inform the kernel of something we want. And so what we can do is that we can define notification on each resource, CPU, I/O, or memory, and we can define that we are going to look at just some process or full process, all of them, and then we can define the two important metrics, the threshold and the window. So if we accumulated more than this threshold nanoseconds, a microsecond of time over the window, then a trigger is fired by Linux, okay? And the way for you to receive the trigger is to poll on the process. Okay? So what's happening here is that we have /proc/pressure/IO, and we are registering a trigger on IO for some process, and if it's waiting for maybe 250 milliseconds over 4 seconds, then we want to get a feedback. Okay? So we just send this information to the file, and then we need to poll the file. So poll is a system call, there is poll, epoll, and other alternative, but the idea remains. This is a system feature to just look at a file and look at something, and if something changes on that, you will be informed. Okay, so you just need to loop, and it's not burning a lot of resources. It's performing. And to get an example, in PostgreSQL we have a way to wait for things. Okay, when we wait for things in PostgreSQL, previously we were doing something like sleep or doing other stuff. Today the wait machinery in PostgreSQL is managed with poll on the system. So this is the same kind of thing we need to do for PSI. So we write to the file and then we receive events and we check the status, meaning that we are going to poll on the file. We can poll several files at once. And then we are informed that something happened. Then we need to look at all the events we received to define if the events, to what files the events are related, because maybe we are waiting and polling on some I/O and full memory and other things. So we need to loop on that, receive the events, and when we have the events, we evaluate if the events are correct, because sometimes you have a fake event, which is just something has been released, and you have no real trigger, just you are informed that nothing happened, but you need to reinitiate your polling, for example. But the one we want to look at is a PRI signal, which is a priority signal, which is not managed by PostgreSQL yet, but I'm going to propose a patch for that soon, because just 3 lines patch and we have benefits from PSI Linux. And so PRI signal is a special signal from the kernel to inform about priority topics. That's all. So far so good, and the only point is that you more or less you need to write code, either C or other things, to be able to poll files on Linux. It's not something you're going to do on bash script. And so either you do your own things or you write your code or you look at other solutions. So what you saw so far is that it's working with /proc/pressure for all the system, but then we have exactly the same thing available for the container group. Okay, container group, C group in Linux are used 100% of the time, because today C group are used by systemd. So when you start your server, you're using C group by systemd. When you use Docker, this is inside C group. When you use Kubernetes, this is using Docker or Podman. This is using C group, and so on. Okay, so you already have PostgreSQL running into a C group, which is convenient. So we can have information from PostgreSQL itself, and also metrics from the system. So we can compare PostgreSQL group and system group, at least. But then also we can improve and get more group into PostgreSQL, so we can better evaluate the distinct workloads. That's why at the beginning I mentioned critical workload, maintenance workload, and so on. Yeah, so what I said, systemd, Docker, Kubernetes, well, everything is in a C group today. So what it brings really is very granular metrics. This point is really, I insist on that because this is super important. This is really the key point, because what we want to do with that is not to observe, monitor, and send a text message to be able to do something some minutes later. What we want to do here is to be informed and get the process, manage that, and we adjust the workload instantly. Okay? So we do not have to send a text message and have an operator doing something. This program is going to work. So PSI provides that, very granular, provide a very easy to use interface. So in /proc, like many things in Linux, or in /sys/fs/c group for everything related to C groups. And next, we benefit from kernel notification. I realize my English accent is really hard for the AI. And maybe for you too, I apologize. So let's get another example here. And here we're going to use PSI itself. And so here I show how to use triggers. And so we are just going to define, I predefine triggers into my base, and so I can after that look at them. And so here I registered some triggers, and the triggers which are registered onto the system are one on workload group for IO resource, on some scope if it's installed for 50,000 milliseconds, 50 milliseconds, and a window of 2 seconds. So the extension also outputs the file path, and so this file path /sys fs cgroup blah 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 up to, you see, io.pressure. This is just a reverse from the system. On the system this is /proc /pressure /io, but here for each cgroup we have io.pressure, cpu.pressure, and memory.pressure. And so getting this trigger registered, we can look at it. And so we're going to use PSI poll, which is an interactive option to just be informed. So if the trigger is fired, we get a message. So it means that if you run vacuum full on one session and you start PSI on the other session, instead of looking at top, you just have to wait, and if there is a notification, you know you're going to exceed maybe your resource and maybe you want to act on the vacuum full. But we can do it more without interaction. So this one is very convenient to do monitoring and to look at things, how they go. But then what we want to do is that we can register triggers with a bunch of triggers associated with a scenario, for example. So we can associate CPU, I/O, memory, get distance threshold, even distance threshold on the same event. You may want to get events if I/O is saturated up to distinct levels. And you get those events notified. And then, instead of starting PSI poll, you can start a worker. And the worker is just going to poll on the resource and apply whatever action you have associated with the trigger. And in this case, the action associated is to kill the process. So what I do is that I start a vacuum full on pgbench account, and at the same time I have a pgbench which is running. pgbench is a benchmark tooling for PostgreSQL, so it's going to connect to Postgres and increase the load, and it requires a source. And so after not a long time, pgbench is consuming a lot of resource, vacuum full too, and so the winner is pgbench because my trigger is going to kill the vacuum full. So here my vacuum full has been killed in less than after 2 seconds, just because my workload does not allow it to run. So I mentioned at the beginning, so this is not on GitHub, this is not on GitLab, this is on Codeberg. You can visit here our page for Data BNPG PSI. The code is not really updated on the website at the moment on this URL, this is another place, but I hope to be able to push that quite soon. Everything is under PostgreSQL license, so you're free to do whatever you want with the code. And that's all. And so I want to look at some future for PSI and PSI. And so one ongoing discussion is to be able to reduce the window in PSI. Remember, it's 50 milliseconds by default for sample. No, sorry, the window of 2 seconds. Apologize, mistake. You remember the window for end users is 2 seconds, okay? And one project is to reduce this window so end users, without being root, can get notification way faster, after 1 second or half a second, for example. The main point is that it's a bit similar to PostgreSQL. When PSI has been introduced into Linux, we didn't know exactly what's going to happen, and it's a little bit defensive or protective. So instead of opening everything, some doors are closed, like the window, to ensure that people are not going to overconsume that and have bad workload on the system just because of the PSI usage. After some years, we have a better feedback on the behavior. We are better able to evaluate the cost of that. And so it's maybe interesting now to reduce the window and to remove some of the constraints for end users. The other interesting point in PSI is the support for eBPF. So eBPF is Berkeley packet filter into Linux kernel, but it's not only for the TCP and for the packet filtering. This is to do many things which are doing input and output through the kernel, I would say. And so the point here is that there is ongoing work to have PSI primitive in eBPF, meaning that you can start and write your own eBPF code, which is sandbox code running by the kernel directly, able to associate with eBPF of each of your C group. For example, you can associate your program with a critical part of PostgreSQL. And so in this case, you don't need PGPSI, but using eBPF, you have a very low-level tool, very powerful, and also sandboxed, so it's very safe to use. And so here you're able to do whatever you want. This kind of setup is very similar to what is done by people like Facebook, where they use this kind of solution to reduce the workload. And for us in PostgreSQL, clearly one of the benefits is the out-of-memory management. Because this is, for example, for people using Kubernetes is super interesting on many topics, but for performances, this is really bad. They do not implement kernel features, and they have several years of lag in this area, and they are not. The support for PSI is just entering right now in Kubernetes in its current version. So we can expect better work in the future in Kubernetes with that, but meantime, using PSI into PostgreSQL or into the system, you can ensure that you have resource and reduce the risk of out of memory, including in a Kubernetes setup, where it happens more often than we want. And future for PGPSI, the tool itself, is to provide, it's very hard to provide something which is going to work for everyone and all situations. So I prefer to focus on providing the key components of what is provided by the Linux kernel, export that to the users, and here the users are developers, so they can just use this primitive to set up their own logic. Okay, they can define, you can define yourself what is a good workload, a bad workload, what action you want to trigger when the trigger is fired or whatever. I just want to implement the logic and providing an API so you can just register your own function to do whatever you need with the logic. And well, another option is to couple that with PostgreSQL 18. In PostgreSQL 18, we have open metrics in PostgreSQL. I mean, we have accumulated statistics which are now an API, so you can use it in your own extension. So you can use the statistics system from PostgreSQL itself to register your own metrics. So one way for PGPSI is to do that. So it means that for DBA, we'll have a single, or she will have a single catalogs where there are metrics, statistics, and also PSI information. And always in the same goal, which is to be able to observe, to assess what we need, and to adjust our workload on the fly if we can. Just two snapshots, two screenshots. One is very basic one. This is a PG benchmark running, and with a top. So we have, this is French, but I'm sure you know the numbers here. Well, we can see we have many processes running. They are consuming 80% of the CPU or 90%, 9%. And well, this is more or less all what we know here. If we look, and if we unfold on top, we can see there are details on CPU with system, nice, idle, weight. This is convenient, but it's a little bit fuzzy information. And this is a view very similar for the same PG benchmark which is running, but using PGPSI. So this time, instead of getting load average per process like in top, I can see, or for each of my group, what is the current status. Okay? And so I know that for running my PG benchmark, most of my workload is really on a workload group. That's convenient. And for some process, and I see that I have really overconsumed stuff because here I'm still up to more than 1.3 seconds plus 0.7 seconds on the bottom. So overall, I'm stalled for 2 seconds on 2 seconds. I'm saturated machine. And many other tiny topics. A last slide for questions if there are, and for you to take the QR codes. And I hope you understood what I said and it was interesting for you.